Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss ballistic galvanometer. Let's begin. What is ballistic galvanometer? A ballistic galvanometer is a specially designed moving coil galvanometer that is used for measuring the total quantity of electric charge in which an impulse is applied to that coil due to the passage of transient current or charge. Transient current, that is the oscillations are not periodic, the oscillations are aperiodic, the transient meaning. And when that transient current pass through a galvanometer, the moving part of that galvanometer experiences an angular impulse and begins to perform angular oscillations about its axis, and the maximum deflection or throw is proportional to the total charge passing through the galvanometer. That deflection is the measure how and what amount of charge passed through that of galvanometer. By taking that deflection, we can easily calculate the amount of charge or current passes through that of galvanometer. Now, what be the principle on which the ballistic galvanometer performed or worked? Whenever a current carrying loop is placed in a uniform magnetic field that experiences a torque, this principle is helpful to the working procedure of ballistic galvanometer. Next, construction of ballistic galvanometer. Here the ballistic galvanometer consists of a circular or rectangular coil of well insulated large number of tons of copper wire wound over that of laminated non-conducting frame of bamboo or ivory. Look here, that one is the soft iron core. Here a mirror, and the torsion head T1, that wire the phosphor bronze, or quartz fiber. Permanent magnet North pole, South pole, these are the permanent magnets. P, Q, R, S, the coils. There will be a spring here, the hair like spring. Another torsion head, T2, the soft iron core, soft iron core. That soft iron core is suspended between the two cylindrical pole pieces of permanent magnets by means of a phosphor bronze, or we can say it as the quartz fiber. To retain the magnetization, or we can say to retain that magnetism, a soft iron core is used, and the magnetic field lines tend to crowd through the core because soft iron core is ferromagnetic in nature, and the permanent magnet creates the radial magnetic field. Due to the strength of that magnetic field increases, and the upper end of phosphor bronze or quartz fiber is attached to that of torsional head, and the lower end it is attached to the hair like spring made up of quartz or phosphor bronze having few turns, and it has various functions, like it keeps the coil in position, and it provides the restoring torque on that of twisting coil, and it gives the passage to the flow of current to that of coil PQRS. This one be the construction of ballistic galvanometer. Now, the other end of that elastic hair like spring is connected to that of terminal T2, and a small mirror M is attached to the suspension, that is the phosphor bronze fiber, which helps us to measure the deflection of the coil by using lamp and scale arrangement. Here lamp and scale arrangements are there. This is the lamp and the scale arrangement. The reflected ray are seen on that of scale, and the distance measured according to the formula of deflection. Let me discuss how the lamp and scale arrangement to that of ballistic galvanometer is helpful to calculate or measuring the amount of current, or we can say the amount of charge to that of coil. Theory: to measure charge from ballistic galvanometer, it is necessary that the entire charge must be passed through the coil before it begins to move. And when a charge to be measured pass through the coil, it is given an angular impulse which sets angular oscillation, and the coil angular oscillation in that of coil, and the deflection is observed. So, suppose that coil PQRS is suspended freely in that of magnetic field of B vector, and I be the amount of current passing through that of coil, then that current carrying loop or current carrying coil placed in that of magnetic field experience a deflecting torque. Here the deflecting torque tau is given as N PM cross B vector, where N be the number of turns of the coil. And PM is the magnetic dipole moment. Which is the product of current and area of that of coil. As the plane of the coil is always parallel to that of magnetic field, and here theta is 90 degree. The cross product, so sin theta sin 90 is equal to 1. Since the field is radial, it always produces the maximum torque. Always theta is maintained as 90 degree. Hence, here theta is equal to 90 degree for radial field, and that field must be radial due to these permanent magnets. Therefore, tau is equal to N PM B sin 90 1, or tau is equal to N IA B, where A is the area of each turn of that of coil. Due to the deflecting torque, the coil gets deflected and the phosphor bronze gets twisted as here angular moment in that of coil, angular moment of that coil is the product of torque and infinitesimal time dt. Angular moment L vector is equal to 0 to tau n b a I dt is equal to n b a 0 to t dt I dt from 0 to t, that is the total amount of charge, 0 to t I dt that is n b a q is the angular momentum of that of coil, and that angular momentum is also written as I omega. L is equal to I omega. N B A Q, where omega is the angular velocity. Now, as a result of deflecting torque, a restoring torque is developed, which tends to rotate the coil back to its original position. If that be the phosphor bronze and it tends to rotate, so an restoring torque is restored. Here let we take, if K, the restoring torque for a unit angle, restoring torque per unit angle of twist of suspension where an alpha with the twist production, that is the twist produced in the suspension fiber due to the rotation of that of coil, alpha, the twist produced here, and the torque on twist alpha with the K alpha with the torque on twist alpha, and work done for an additional twist d alpha, the K alpha d alpha be the work done for an additional twist d alpha. Hence, the work done in twisting the suspension fiber between the initial and final position, therefore, the work done in twisting the suspension fiber between the initial and final position will be that from 0 to alpha k alpha d alpha, which is equal to half k alpha square, where alpha be the angular deflection of the coil in the final position, the total twisting. Now, we equate this work done to the decrease in kinetic energy. So, equating this work done to the decrease in kinetic energy, we have decrease in kinetic energy, that is half I omega square, that is equating to that of work done half k alpha square. Look here, as we know, if t be the time period of oscillation of the coil, time period of oscillation of the coil, then the time period of oscillation is given by 2 pi under root of I by k, where I be the moment of inertia. Here I be the moment of inertia. T is equal to 2 pi under root of I by k, or t square is equal to 4 pi square I by k. Here the moment of inertia I is equal to k t square divided by 4 pi square here. Now, that value of I is put here, half cancel out. So, in place of I substitute okay. Look here, I omega square is equal to k alpha square. Let that be a equation. Let equation number 2, and I is equal to k t square by 4 pi square. Let equation number 2. Now multiplying, that is 3, multiplying 2 and 3, multiplying 2 with 3, we get that will be I square omega square is equal to t square k square alpha square divided by 4 pi square, or I omega is equal to t k alpha divided by 2 pi. That equation number 4. Look at that equation number 4 and equation number 1, I omega is equal to NBAQ, I omega is equal to TK alpha by 2 pi. And comparing equation 1 and 4, comparing equation 1 and 4, we get NBAQ is equal to TK alpha divided by 2 pi, or Q is equal to T by 2 pi K divided by NBA do alpha. Or Q is equal to the constant K, capital K into alpha. Here K is equal to capital K, that constant, small k into T divided by NBA 2 pi, small k with the restoring torque for unit angle of twist of suspension of that wire, T with the time period of that of oscillation, N with the number of turns, B with the magnetic field, A with the area of the cross section of that of coil, 2 constant, pi constant. That constant value is known as ballistic galvanometer constant. Ballistic galvanometer constant, and that one be the quantity which is directly proportional to Q, directly proportional to alpha, means charge is directly proportional to the angular twist. So in this way, what amount of charge flown throughout that of circuit is calculated by using that equation, by using that angular twist. The amount of charge flown through that of circuit is easily calculated. Now a technical term that is used for ballistic galvanometer, which is known as sensitivity. According to the sensitivity concept, we can easily point out what the performance of that of galvanometer be. So sensitivity, ballistic galvanometer is said to be sensitive if it gives a large reflection whenever a small current is passed through it or a small charge is being sent through it. For a given ballistic galvanometer, the charge is equal to K alpha, K with the constant, or K is equal to Q by alpha. That term Q by alpha is known as the charge sensitivity. Charge sensitivity, or we can say that is the ballistic constant, or ballistic constant of ballistic galvanometer. Ballistic galvanometer. And the charge sensitivity is defined as the charge required to produce unit deflection. So we define two technical terms, one is charge sensitivity and another one is current sensitivity. So charge sensitivity, this is the charge required to produce a unit deflection. Unit deflection, the deflection per unit charge, that is charge sensitivity, is equal to alpha by q. Okay, alpha by q. So here how alpha is measured? We know q is, the value of q is equal to T by 2 pi k divided by NBA alpha, as we get here T by 2 pi k NBA into alpha. Now how alpha is measured? Suppose in the lamp and scale arrangement, let me take in the lamp and scale arrangement, that scale is placed at a distance of, let d distance from that of mirror, and that mirror is attached to that of phosphor bronze suspension fiber. Now when that coil deflects through an angle alpha, then the reflected ray turns to an angle 2 alpha, and that reflected ray spotted to that of scale at a distance of x. Spot of light deflects through a distance x on that of scale. So tan 2 alpha, here tan 2 alpha is nearly equal to, tan 2 alpha is equal to x by d. Since the deflection is very small, so we calculate 2 alpha is equal to x by d, nearly equal to. So alpha is equal to x by 2d. So in place of alpha we can substitute x. We know what exactly the distance throughout that of scale, and d with the distance between the mirror and that of scale, we know it. So by putting these two values we can easily calculate the value of alpha. If we know alpha, then put it the value of alpha, and we have the corresponding charge sensitivity term. So here charge sensitivity is equal to alpha by q. So alpha by q is equal to, here in place of q alpha cancel out, so the term exists here, that is 2 pi NBA divided by Tk. These are for charge sensitivity. Then current sensitivity, current sensitivity of a ballistic galvanometer is defined as the deflection produced in the galvanometer per unit current flowing through it. This is the deflection produced in the galvanometer per unit current flowing through it. That is current sensitivity is equal to alpha divided by I. When a steady current I flows through the ballistic galvanometer, a steady deflection alpha is produced. So, here deflection of torque or deflecting torque is equal to the restoring torque. Deflecting torque, that is NBIA, which is equal to the restoring torque K into alpha. So, here I is equal to K by NBA into alpha. When in place of I we substitute that value, so we have NBA by K, alpha cancel out. In this way, current sensitivity is calculated for a given ballistic galvanometer. If we compare current sensitivity with charge sensitivity, so what we find? From the concept of current and charge sensitivity, we have charge sensitivity is equal to two pi by T times of current sensitivity, 2 pi by T times of current sensitivity. Charge sensitivity is equal to 2 pi by T times of the current sensitivity. So, with the help of this visual expression, we understand ballistic galvanometer, its principle, construction, theory, and sensitivity. Basically, as charge sensitivity and current sensitivity, relation between charge sensitivity and current sensitivity. So, with this useful and informative notes, let me wind up this session. Thank you.